Hello, Arizona State University. This is L Space Academy Group 4, Project Linus. We are very excited and eager to share with you all of our hard work and research we have done over the course of this past semester, and we hope you're impressed with our project. Our team is comprised of 5 students, all of which are from UCF. Our team members include Alex Rodriguez, Cody Schultz, Jennifer Nolu, Steven Schroeder, and me, Nicholas Alban. Now I'll pass the presentation over to Jennifer so she can tell you about our mission and our objectives.
Our mission is to seek answers to the ongoing investigation of whether or not life exists beyond Earth, particularly on the planet of Mars. Our Linus lander will travel to the home plate of the Gustav crater on Mars by spacecraft to make a soft landing on the surface of the planet. And Linus will record data with the SIVA instrument package once it lands within our target ellipse. Our mission objectives are to land our payload safely and upright, as well as collect data via SIVA to determine the presence of extant or extinct life on Mars. And now I'll pass it to Cody to discuss our landing site.
As mentioned, our project is a small mission of opportunity designed to make a soft landing in Gustav crater on Mars to explore the home plate feature for signs of extinct or extant Martian life. Opaline silica deposits were first discovered on Mars in 2007 by the Mars exploration rover Spirit, which was adjacent to the home plate feature in the inner basin of the Columbia Hills of Gustav crater. The discovery of opaline silica and the presence of successive layers of vesicular basaltic rock has been interpreted as evidence of past volcanic hydrothermal activity. Scientists later discovered the significance of the morphology and its similarity to active hot springs and geyser discharge channels on Earth and El Tachio in northern Chile. Furthermore, these scientists also found that the digitate silica structures at El Tachio were produced by a combination of biotic and abiotic processes, leaving open for suggestion the possible direct or indirect influence of biotic processes in the formation of the home plate feature. Our group has recognized that hydrothermal features have long been prime candidates for the search for fossil life on Mars. And we plan on using this mission of opportunity to follow up with these earlier observations from the Spirit rover. In particular, we hope to investigate the home plate feature and adjacent features for evidence suggestive of microscopic fossils and protein structures. I'll pass it over to discuss our payloads.
Our first minor payload integration is the accelerometer. We are going to use a triple-axis accelerometer to be able to allow the Linus lander to know how it's linearly or angularly accelerating, as well as whether it's tilting to ensure that our lander lands upright on the home plate of the Gustav crater. And now I'll pass it back to Cody.
In selecting our main payload, we looked back to ESA's Rosetta mission, and in particular the Philae lander. On the Philae lander was an imaging suite called SIVA. So SIVA is composed of 2 ultra-compact and miniaturized microscopes, one operating in the visible and one operating as an IR hyperspectral imaging spectrometer. Both instruments are designed to characterize the texture, albedo, and the molecular and mineralogical composition of Martian surface samples. The optical microscope, to go into detail, has a spatial sampling resolution of 7 microns, whereas the IR microscope has a spatial range of 1 to 4 microns and a spectral sampling of 5 nanometers. This allows for the identification of most minerals, ices, and organics. The resolution of the imaging system will also allow for the identification of many species of potential bacteria and other microbes that we find here on Earth, as well as their fossil remains. The resulting data collection will help to characterize and contextualize the organic, volatile, and mineralogic history of the home plate feature, and will also help to elucidate the potential biological history of the home plate feature in Gustav crater. Now let's learn a little more about the engineering systems for our payload, or for our lander.
So in order to fulfill our need for a purely mechanical landing, our lander will release a parachute upon detachment from the gondola, from which it will perform a soft landing into Gustav crater and will release the payload by having the walls open outward, both revealing the instruments and righting ourselves upward in the event of a rough landing so that the SIVA instrument package faces downward into the soil. Optimally, that won't happen, but we also have a secondary base plating along the bottom of the lander to protect our instruments from the force of impact and from other sharp objects. To talk more about the lander's design, I'll send it off to Alex.
All right, so this is our lander design. I designed it in Autodesk Inventor, and as you can see, it's a bit of a more rudimentary design, but it is more to show that the dimensions of the rope, the lander itself, and also the parts of it. So here on the top we have this cylinder. This more representative of just to represent our descent module. It's in particular it's supposed to represent our parachute, and it's just supposed to give us tolerance for that. So because the thing is, from the top of the cylinder to the bottom of this base plate is 33 centimeters. So we just want to make sure we have this measured out, and also from the total diameter of the cylindrical base is 30 centimeters as well. So we just had these dimensions set out, and we know it will fit in the gondola. Now coming down from this frame, we have the square frame, payload frame, where our payload will be contained. It's square because it's just simple, it's easy to CAD, and also provides lots of space. I also have, in addition to, added an additional plate right here just for additional protection to the payload itself. And on the sides here, we have foldable sides, which will be deployed upon landing. These will help correct correct the rope, the lander itself, if it lands on either side. And for now, we haven't settled on the deployment system, and we would finalize that during prototyping stages. So for now, it's just blank with no springs or anything. Keeping to go further down, we have the bottom base plate. This is thicker than the rest of the plates to help protect, as Stephen mentioned, to protect against rocks. And in between the two will be cushioning material to help cushion the blow upon impact. And here's the annotated design. We have all the parts annotated with all their measurements, along with pins and stuff that were featured in the design itself. This will be featured as a PDF along with the STL files for the rest of the parts and assembly. So, and these will all be provided alongside the PDR, so you can have them. And the STL files will allow you to 3D print the parts, and in addition to viewing the model in 3D on the computer itself.
And with that, we want to conclude our presentation, and thank you for your time. We included UCS original mascot, the Citronaut, on here too, because it seemed very appropriate for this talk. The Citronaut is actually UCS first logo when it was founded as the Florida Technological University, which was a university that was supposed to supply the scientists and engineers for the new NASA program out at Kennedy Space Center, but it's since been retired, but it's still a favorite among a lot of us. But with that, again, thank you for your time. We want to encourage you to read the PDR we produced, and we hope you like what we wrote. So thank you again, and it's been fun.